Hi, my name is Andreas, and in this video I will walk you through a small project we just released in the marketplace for you to use. In this Unreal Engine 5 project you will find a little robot who comes with features beyond simple movement. He has a jetpack, you can print a new one, and he has the ability to interact with buttons and switches. This project was done internally with mainly 2 people. We partnered with game developers for the character and for some of the modular pieces. It's a great project for those picking up Unreal Engine for the first time or for game developers looking to try out new features in Unreal Engine. We made use of a lot of new features like Lumen, Nanite, World Partition, Enhanced Input System, Control Rig with full body IK, and many more features in a small 1 GB big project. I will give you a quick rundown of what you find in this project, including some neat tricks we used. We tried to make this a small sandbox to tinker with, and that can get you started, but it's not a fully fleshed out game sample. This video is also not a step-by-step tutorial to explain how to build it. I will go quite fast through some of the more interesting parts of the project. We tried to keep all parts easy to digest and added a lot of comments so you can check it out at your own pace. Here and there we left some hints how you could extend it or what you would do in a fully fleshed out game. For level designers, there are already some game elements you can place to build puzzles with. Or you can create new game elements on top of the component-based interaction system we built. First of all, you can download it from the marketplace, and we will put the link also in the description. When you open up the project for the first time, you will see this hint. The main map uses World Partition even if it's a very small one, so you can see only this area. You can load the cells by going to Window, then World Partition, select all cells and load. Now we see the full map. As the map is not big, we have only 4 cells here, and in the world settings you can define the cell size and loading range, and you could even have several ones with different density. All actors in this test room we made are set to always be loaded. Other actors, like the building in the background, is loaded depending on the location on the grid. The building is made with packed level blueprints, which consolidates groups of meshes down into easy to manage blueprint actors. We can edit them here in the main level, like removing parts and then commit the changes. If we would have more than one of this instance in the world, it would also change for all of them here. We also use one file per actor. This turns every actor into a unique file, which allowed us to work on the same level together at the same time. This project uses Lumen, the new global illumination solution in Unreal Engine 5, which is enabled in the project settings rendering. We also switched to virtual shadow maps, which are in beta. Remember that Unreal Engine 5 is still in early access and there are several changes and performance optimizations to come. The result is already astonishing and gives us real-time light and shadows not seen before. Almost every actor in the world uses Nanite, our virtualized geometry. That includes our high-density rocks, but also low-poly modular building pieces. So Nanite is not only good for high polygon meshes, but a general optimization usable in every art style. It always tries to have the best resolution for you on screen, so we actually didn't bother much with LODs. But what Nanite can't do yet is materials with world position offset, mask, or translucent materials, so our trees here are not Nanite. As virtual shadow maps get invalidated, we needed to redraw when stuff moves. We have 2 materials, one with the function doing the wind, and one without any world partition offset. In the mesh, we have 2 LODs, where LOD 1 uses the material without the wind movement. And depending on distance that we can control, the moving trees get replaced by a static tree. That is a performance optimization we did for the virtual shadow maps. We included several materials and material instances in the project and optimized it for draw calls. So there is one solid base material handling color, emissive, AO, metallic, but also leverages vertex color. And we have several different meshes for our building pieces and props, so we use a material collection where we can easily change properties like, for example, the color. Let's take a look at the landscape material. In that we blend different textures like rock, people, sand, and grass, but also outputs the result into a virtual texture. That virtual texture we can now use in the rock material to blend the bottom of the rock with the landscape material, which looks quite neat. Let's briefly get back to the foliage. Beside some wind movement, we wanted to have the grass and fern reacting on the player. So we made a material function that uses the material parameter collection that has the player location to calculate an offset to write the fern away from the player. The character writes the location into the collection on tick. And this is how it looks like. We wanted the grass also to react to the player a bit, but in a slightly different way, and you can find the setup in the grass material. And now let's dive a little bit deeper and let's check out our character. Our little robot here comes with a skeletal mesh, a skeletal, and several animations like idle, inactive, walk, run, fly. And we have an animation blueprint done in a very modular way. It also comes with a physics asset we made, so we can set him to Ragdoll, but we will also use it for partial Ragdoll setup. And last but not least, we have a control rig that's using the new full body IK solver, so we can correct his foot movement, and we will also use it for button pressing. So here he is. He can walk and he can jump. And when we move over to this little button, we play an animation that we correct with the control rig. And he has a jetpack, which we will explain in a second. But let's start with the animation blueprint, which has a state machine for ground locomotion, for air locomotion, an upper body slot to play animations in, which we blend only on the upper body, an inactive state, and a control rig to adjust some animations. I want to show you some tricks. So for example, in running, there's a blend space that has one axis blending between running and walking and a lean. So where do we get the data for the lean from? When we take a look at the update animation event, you will find a calculate lean function. And in this function, when we take a look at that, we have a previous and the current, and we take the delta from the rotation, use an F interpretate to smooth it out. And that's what's driving our animation. So that's pretty simple and neat. So let's take a look at the air locomotion, which is a bit more complex because from falling, we can go into the jetpack. But I want to draw your attention to the land, because we have a land that is going into the stand mode and a land that's going into a running mode. How do we differentiate that? So in the transition, we have a Boolean if movement input is done. And in the event graph, we can actually grab the input vector. And if the length is 0, we just set that. That's pretty rough, but it gives us a pretty nice result. And we want also to have more impact, so we make an animation notifier which get fired and that plays a camera shake. And this is how it looks like. So it's a bit subtle, but I hope you can see it in the video. And here is without movement input. And when we have movement input, he goes into the running. So let's go back to our animation blueprint where we left off and talk about the upper body slot. So there's an upper body slot where we can play a montage in for pressing the button, and we use a blend per bone to determine it's only played on the upper body and not on the legs. And then we have a bool that switches to an idle animation, really rough. But then we have a control rig that do some neat tricks. So I want to show you that. So first of all, let's see what it does. So when we move over here to our fake landscape, you can see the foot are placing properly on the ground. And this is done in the following way. We have controls that we first place where the feet animation is. And then we have a function that's tracing from that controls down. And when we hit something, we take the Z component and use an interpolate where we can increase and decrease speed, so we can slowly move toward that. And then we use an aim math for the rotation with an up vector, so we know how we would rotate the feet on the ground. And back in the big graph, we do this for both feet. And then we use the controls and we add the offset of Z and the rotation and use a full body IK that does the magic. And this is how it looks like. It's pretty awesome. Next, let's talk about the logic for the character. It uses a blueprint for the character based on the Unreal Engine framework, so the character comes with a capsule, a skeletal mesh, and a movement component. In the character movement component, we did some adjustments like how fast he can run, how high he can jump, or the air control until it felt right. We also added a camera and a camera boom. I will come to the camera in a second. And then we added a jetpack, a skeletal mesh, and a Niagara effect for the thruster. This will be also part of this video. As well as the MetaSound we did for the thruster that's reacting on gameplay. One other new thing we use is the enhanced input system, where you can find some assets for the actions like button presses for Boolean or for movement a 1D axis. And then there is an action mapping where we map those actions to buttons or gamepad input, etc. One cool thing here is we can now add triggers and modifiers. So we added a dead zone, for example, for the thumbstick. And in the project settings, we switched from player input to enhanced player input to leverage that. Back in the bot, when he's possessed, we add the mapping context, and now we can use the events, which comes with much more execution pins and much more options we can use. And this is basically the whole setup for the input for turning and movement. Let's go to the jump and talk about the jetpack. The jetpack is like a double jump. So when you jump again in air, you stay there a bit and can glide. So let's see how this is done. So on jump, we check the movement component. And if we are walking, we just use the character jump function. If we are in air, we toggle the jetpack. And if the action is cancelled, we stop the jumping and we stop the jetpack. The event on landed comes with a character and we reset our jetpack. So let's take a look in the function. So when we reset, we just set back the time, how long you stay in air. We say it's active, and then we change the air control and we toggle the thruster. We also toggle the sound. So before we go further, let's take a look at the Niagara effect here for the thruster. It's a very, very simple setup. So what you can basically see here is a spawn rate. And then we have also an initialized particle with a color, and we add a velocity and a very simple material. The only special thing here is that we use a skeletal mesh location, which we sample for the sockets. So when we take a look at our skeletal mesh here, we added 2 sockets, and now instead of placing them by hand, it's automatically sampling them and positioning them in the right place. Next, let's talk about the MetaSound, which is super cool. I'm not a sound designer, but MetaSounds give you a really great opportunity. So imagine this being like a material editor, but now for sounds. So what I did here is I recorded 3 sounds. One for ignite, one as a loop, and one for wind down. The start and the end is actually my drill, and the loop is me making car noises on the microphone. So now we play this ignite sound when the sound starts, and after that, when it's finished, we start the loop sound. We also use an envelope to manipulate a little bit the pitch. Then we implemented a trigger, and when this trigger is called, then we play those winding down sound. We also use this trigger to stop the loop and to stop the ignite. And this is how it sounds. So in the bot, we call this trigger, and now we have an adaptive sound that we do not have to change when we change the values how long we stay in air. To see how long we stay in air, we have to take a look at the tick, where when the robot is active, we update the jetpack. Here is a number we're reducing over time, and we use also, after normalizing it, to get access to values from a curve. This curve modifies how much thrust we apply. So at the beginning, we push him up, and then the thrust depletes. And the designer can modify this easily. So after that, we also change the thrust amount in the particle effect. I haven't shown that. So we have a user value thruster strength here, which we add for the lifetime. And then if the thrust time is over, the jetpack gets disabled. So this is how it looks like. So character, camera, and control are super important for this kind of game. We already talked a bit about the controls, and we implemented a very much too simple camera. So when you do a full project like that, you might need more than this. But let's take a look what we did. So in this project, we have the camera and a boom, and we can adjust the angle. So on the event graph on tick, when he's active, we update the camera. What we do here is we trace upwards of the character, and if you hit something, we move the camera in. If not, we take a look if the character is currently flying, and then it moves out a bit. Then we use an F interpretate node to smooth it out a bit, and setting the arm length. That's basically it. It's not enough for such a project, but it should get you started. So now you can see here maybe very subtle how it moves out, and if we move under this little ramp here, it moves in a bit. What we also did is we clamped the camera jaw, but to talk about that we have to go a bit deeper. So under framework you will find a player controller. Player controller in Unreal Engine is like the brain of a character making the decisions, while you can see the character itself as the body executing it. So here in the player controller it also controls a player manager, which we set here to clamp. We also set the input mode to game only as we don't have UI, and we hide the mouse cursor and we spawn UI. This icon shows you that this is executed on the client. So here normally would be the input. So we have the pause input, for example, here, and now it can get confusing. Normally you would maybe have the input for your character here as well, but we implemented our input completely in the character. We made a conscious decision about that because this is a single player game with one character only. But in the moment you do multiplayer or you have several characters, you maybe want to do that in a different way. But for our little sandbox project, this is a good start we could extend later. We really wanted to have a unique feature for this sandbox game, so we tinkered with printing new bots. So you can print a new one, jump on the head of other ones, they can go to Ragdoll, and if too many on the scene, we can dissolve them. So let's take a look. In the bot, in the moment the player presses the button, the capsule gets first set to no collision, and the mesh itself gets set to collision on. For that, we have to take a look at the physics asset. So here in the physics asset, we made a setup with some bodies. We set the linear and angular damping, and for some of them we even offset the center and adjusted the constraints so they fit the body. For the head, we implemented a static mesh so you can jump on his head. For the neck itself, we also added a motor so this head can stay up. Back in the bot now, we set it simulate, but only the head. Next, we detach the camera boom so it stays where it is and doesn't follow the character. Then we set it to inactive so the animation is played. We start a timer to check for Ragdoll and set it to looping. We will talk about that in a second. Next, let's talk about the materials. So we have a material array here. So in construction script, we go over the Jetpack and the character itself, which has two materials, and add all of them in a material list. And here we iterate over them, set the emissive, and we set the mood. I want to talk about the mood a little bit. So here's a material with different facial expressions we could use. So this is done in a way that we use a Flipbook and an atlas. So a little bit of mass, and then we have an atlas with his faces. We are actually only using two of them. Feel free to use the rest as well. And then after a short delay, we cast to the game mode. We would spawn the player. So be careful with the casting because it's a hard reference, but in our case, the game mode and the character needs to be in memory anyhow. So here we spawn the player at the active spawn pad. Let's go shortly back to the Ragdoll check. So when we have started the Ragdoll check, there's a macro, and in this macro you can find 3 reasons why we go in full Ragdoll. The first reason is the velocity of the character. So if we are too fast, we go into Ragdoll. The second reason is a trace below the character and seeing if we have some surface below us. If not, we go in Ragdoll. Third reason is when the head moves too fast, and that is because of a bug we had. Here you see the decapitation if we do not check for that. So now we have the 3 checks in place. So if one of those is happening, we go into a full Ragdoll here with set simulate physics, and then we clear the timer. So now let's go to the game mode where we do the spawning of the spawn pad. So that can be found in the blueprint folder under framework and then game mode. So here we have the function, and the first thing it does, it spawns a player at the active spawn pad. We will come to that in a second. We also see get maximum bots here. This is actually a function library we made because we needed the amount in different places in the project. This function library could be extended or even use a data table. But let's go back. So after the spawning, we have a list of spawned characters here, and if that exceeds the max amount, we first dissolve the first one in the list. Then remove it from our list and we add the new one, and we increase the spawn counter. Let's go to the dissolve to stay in the robot for a second. So in the dissolve, first we set simulate to no and then the mesh to no collision. And now we spawn our Niagara dissolve effect. And again, this effect is a pretty simple one. When we take a look at the Niagara effect itself, we have an instantaneous spawn burst, which with a lot of particles. We have a curl noise, a gravity force, and a renderer with a simple particle effect with color. And then we sample the skeletal mesh, so the initial particle position is coming from where it's attached to. So that's basically it. When we go back to the bot, what we also do is we change the color with the hue by index. So here again, this is the get max bots function we are using. And this instead of setting the color, we're setting the hue, which is easier setup for us in this case. So back in the dissolve effect, we make the jetpack and the mesh invisible and set the lifetime of this actor to 10 seconds. So after that, it gets deleted. So in game mode, when we go to the beginning, we have to take a look at the spawn of the player, which happens in the spawn pad. So let's take a look here. Before we go into the code, let's take a look at the thing itself. So here we have a camera we will use, and we have a ring we can move up and down, and the ring also has a plane with a holo material we can switch on and off. So when we move this back, we can go through the steps that are happening now. So in spawn player that was called by the game mode, we first spawn the bot, and that gets the index, which also defines the color. And then we process this with a player controller, and we start the animation, which is done in the event graph. So first we switch to the camera of the spawn pad to have a nice angle. Then we disable the input so the player cannot run away and enable the visibility of the hologrid. Now we use a timeline for the ring movement and the slice effect. So the ring goes slowly up and fast down. So back in the graph, we use this to move the ring up and down. And now we take the Z component of that movement and feed that into an enable spawn effect function we have in the bot. So let's take a look at that. So here, back in the bot, we iterate again over our material. We tell the material that now the printing is enabled, and we give this Z value we can now use to make the printing effect. So when we take a look at the bot material, it's a very simple setup. Here we have an emissive and a mask, and we have this function that is calculating the spawn. So when we take a look here, we now use the slice Z, which is the position of the ring, and the dot product with an upward vector, and this is how we calculate the mass. To fake the interior of the robot, we just take orange here, and then we use this as an emissive output. You could change the color depending on the robot, but we didn't do it. So here we are. Let's go back to the spawn effect itself. So now we printed it, and after that, when this is done, we enable the input, and then we set the camera to the robot. We also disable the visibility of the grid. And now the end result is we can spawn robots. If they are too fast, they go to Ragdoll. We can jump on their head. We can walk around, and we can spawn right now up to 8 different ones until the first in the list gets dissolved. This project also comes with a nice interaction system based on a component. So the robot can run around and can activate things like an elevator, press buttons to open doors, have plates reacting to him, moving platforms, and many things more. So let's take a look at that. So under abilities, you find an interactive component. In this, you mainly find 4 functions. 2 to disable and enable that it is interactive, 1 to start the interaction, 1 to stop the interaction. So it has a boolean to remember if it's interactable and calls an event dispatcher others can react on. So the same is for disabled ability. On start interaction, it checks if it's interactable and calls an event dispatcher. So on stop, it also calls this event, but with setting it off. So now let's see how this is implemented in a game element, which you find under blueprints, game element, and then, for example, the pressure plate. So in the pressure plate, you have not only this component we made, but it has also a trigger box, a base, and a plate we can move up and down. So when we take a look at the trigger box, we have an object channel called trigger here, which we added to the project settings. Now we can fine tune a little bit what's overlapping with it and what's not. So on event graph, we have an event for begin overlap, in which we do not care what actor it is. In the moment something overlaps, we take a look at the actors. If something is in it, we do use a gate for blue once, and then we change the material, and we start now this interaction.
Then we use again a timeline to move the plate up and down. If now something ends overlapping, we check if something on the plate is left. And if not, we first enable the gate again so it can be enabled again. We set the material and now we stop the interaction. Next, we need something to react on the trigger. So for example, the door. The door has an array of triggers implemented that are exposed on spawn, so a level designer can set the references as well as an integer how many of those triggers needed to be activated. At begin play, we iterate over the triggers, take the interactive component and assign an event on the onInteract. So when the interaction starts, we can now increase the amount of triggers that are triggered. We compare that with the needed triggers, and if this is true, we can open the door. If the interaction stops, we decrease the amount of triggers and close the door. And we use a timeline to move the left and right door wings. So in the level editor, it looks like this. So now we can take our door and just drag it in, as well as our pressure plate we have taken a look before. So with both in place, we can select the door, go to the details, and here we have the exposed triggers. We add one to the array and we can pick the plate. We also say it's only one plate that is needed to be activated. So now when we stand on that, it opens. Next, let's take a look at the button, which using the same system but is slightly more complex. So when the player presses a button, the robot presses a button and plays an animation. So let's start with the button itself. The button also has a trigger area. This time it's from type trigger, and in the collision settings, it's only overlapping the pawn and it ignoring everything else. So when the event overlap is fired, we start something we call character orientation check, which is also implemented in the interaction component. It starts a timer that checks roughly if the player is facing the object. So we compare those both positions, use a dot product, take a look if it's roughly facing that. And if it does, we say the interaction is enabled or it's disabled. We use the do once gates to ensure it's only triggered once and not several times. So back in the bot, we also have to remember the interactive bot to start the montage later. So we cast here again, not very nice, but it's not a problem in our case. So on end overlap, we stop the check. And in begin play, we assign an event to the toggle interactivity to display to the player that he can now interact with that. For that, we use a widget component that is set to be drawn in screen space and has a little widget assigned to it. So this is just saying press E and it's set to 200 to 50, which is the same as a draw size. Now for the animation, we also need to know where the button is. So for this, we use an arrow component. So this one here is a position where we want to point to, and then we feed this into a variable that is stored in the interaction component we will later use in the character. Other than the pressure plate, the button doesn't start the interaction, but only reacts on that. The bot is the one who's starting it in the moment the player presses the interaction button. So now we take a look on the actors that are overlapping and we take the first one. That's not very sophisticated. We assume that there's only one in range. Otherwise, we would have to sort or give feedback to the player. Next is we take a look if the interaction component is implemented and we take this position we will use for the animation later. And now we start the interaction. And the button is reacting on that. And the first thing he's doing is playing an anime montage on the interacting character. So the question is, why is the button playing it on the character and not the character itself? So the reason is we want maybe to think about having other things than just a button, like a lever. And then every object would have different animations. So let's take a look at the montage here. And you can see it is played first in the upper body slot. And it has a curve that is blending from 0 to 1, how much key we want to blend into this animation. So let's go to the animation blueprint. So here it's played on the upper body slot. And next thing we need is to get the position in world space where the button is. And we stored that in the character, so we can take that now and feed this in the animation blueprint into the control rig. So let's take a look at that. So here in control rig, you can see we take the rotation of the index finger from the animation and set a control with that. And we take the world position of the button and set the control to that position. So now with this, we can use it as an effector on the index finger. Plus we are using this curve in the montage to blend in and out of the key. And the curve data is stored in the scheduled mesh. So now we have a handmade animation that's adjusted to the environment depending on the orientation of the character. Check out the project to learn more, like about these platforms that are using a control rig component and a little bit of math and a Verlet node to add juiciness to its movement. Or this cable actor that's using a spline mesh component so you can really easily draw some cables into your level. The project also comes with a plugin. If you enable the plugin content, you can find that in this folder. If you drag it into a level, you can give it a size and a grid size. You can add also a floor mesh, and that generates room for you. So this is actually what we used to generate the room that's there in the middle with custom meshes. The music you are hearing is done in MetaSound, and it's such a great tool that even someone like me who has no idea about sound could do this. So I used 2 sound generators, some envelopes, some filters, and tinkered my way through triggers and some randomness. So now I have a sound where I can even adjust some things, like the speed. One additional thing I did here is we implemented a game instance so we can play the music persistence even if the level changes. So in project settings, under maps and modes, we added our own game instance. And this game instance is also used for a small save game system. So the player can collect these orbs and the location and the inventory gets saved. So when he collects this, we use an interface to communicate with the game instance, where we then add and remove that to the player inventory and from the map. We added a lot of comments, so take your time in the project to dive deeper and see how this is done. The project also contains a pause menu, a loading screen that fades in and out, and a tiny main menu. It should show you how all those little systems can work together. We hope you enjoy this project as much as we did making it. We plan to update it for Unreal Engine 5 release and would even have some features in mind to upgrade it if this is helpful for you. So we would like to hear from you in the comments or our forums and show us what you do with Unreal Engine or with this little robot. So this wraps up this video. Download the project from the marketplace. You will find the link in the description. Happy tinkering and see you next time.